Okay, so you've learned about the first law of thermodynamics and the second law of thermodynamics. So we are now moving into the third law of thermodynamics, which states that the entropy of a pure crystalline substance at 0 Kelvin is going to be zero. And the unit for entropy is going to be, let me put this here, joules per Kelvin dash mole. Okay, so if you have, like, say, a sample of aluminum and you take it to outer space where it's basically 0 Kelvin, the amount of disorder would be very, 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 very low, non-existent, because it would be basically standing still, so there is, no microstates available other than the one that it has. So we would say in this case that the S is zero because there's no disorder at that point. Now, understand if you look, there's a table, I believe, in your book that gives you the values of delta H, or the heat of formation of various compounds and elements. And then you also have a different set of values for entropy, all of which are measured in joules per mole Kelvin. And those values are based on the fact that 0 joule mole Kelvin is based on the entropy of that substance at 0 Kelvin. Okay, so the heat of formation you've learned about last semester for elements at standard state is 0 kilojoules, but S at standard state is not necessarily going to be zero. Now it could, but most likely it's not going to be. Okay, so if you look, for example, in the table, you will see that aluminum solid, okay, has a S. The degree symbol refers to 298 Kelvin, that temperature, and the value of S for that one would be 28.3 joules per Kelvin dash mole. And they measured 28.3 with the assumption that aluminum at 0 Kelvin would have an entropy of 0 joule per Kelvin mole. So that's where that value of the 28.3 comes from. Okay, using the fact that it's 0 at 0 degrees, 0 Kelvin. And this equation should look very familiar to you. It's on the handout, and we're going to be doing some calculation involving this. But the change in entropy is equivalent to the sum of the entropies of the products minus the sum of the entropy of the reaction, taking into account how many moles of each there are. Just like you do with heat of formation when you try to find out what delta H is. And we're going to do some of those calculations in a little bit. But before we do that, we're going to talk about Gibbs free energy. So what is Gibbs free energy? I don't want you to think obsess too much over the definition of what Gibbs free energy is. If you take a thermodynamics class in college, you'll learn more about this. You might learn more about it in your physics class. But what essentially Gibbs free energy is the energy available for work, aka used for work. It would be like, say, the amount of energy you have remaining to turn on the flashlight, or the amount of energy you have to heat up the food on your stove. Okay, but we really use this to tell us about the thermodynamic favorability about the process. So the equation that we use to relate entropy and enthalpy is this equation right here. Okay, the change in Gibbs free energy is equivalent to the change in enthalpy minus the temperature times the change in entropy. And be very careful because the units for delta G is usually in kilojoule per mole, one of those. Delta H is in kilojoules, whereas T, of course, is in Kelvin, and delta S is measured in terms of joules per Kelvin. Okay, or it could be kilojoules per mole for this one, and joule per mole Kelvin. Depends on the situation and what values are given to you. Okay, so with that in mind, oftentimes when I give you the values of delta H and delta S, you need to make sure that the units cancel properly because you have to make sure that both of these are in kilojoule or both of them in joule, depending on what the situation calls for. So what essentially you need to know is that a positive value of delta G means that it is thermodynamically unfavorable. Like the reaction will not happen without outside assistance. And a negative delta G implies that it is thermodynamically favorable, meaning that the reaction will happen without outside assistance. It might not happen quickly, but it'll happen, over a long period of time. Okay, if it's not happening quickly. So with that in mind, the truth of spontaneous processes is that delta S for the universe, when we say spontaneous, we're saying thermodynamically favorable, like processes that will happen. Delta S of the universe is positive, and the change in free energy, in Gibbs free energy, is negative. And since those are both part of laws of thermodynamics, you can pretty much say everything all the time, always. So delta S of the universe is always positive for any process that is thermodynamically favorable, and delta G is always negative for a thermodynamically favorable process. Okay, so we're going to be doing some calculations involving delta G in just a moment, but do understand that just like heat of formation, the free energy, the Gibbs free energy of any element is zero under standard conditions, which would be 298 Kelvin and 1 atm. And you can calculate the value of delta G as the sum of the change in free energy of the products minus the sum in the Gibbs free energy of the reactant. And once again, we'll be doing some calculations involving that shortly. So it is important to understand that the value of delta G, does change depending on the temperature. Okay, so if you increase, if you increase temperature, that's going to increase the magnitude of the T delta S term, and that means that the delta S would have a greater impact on what delta G is. Okay, but if you have a lower temperature, that's going to magnify the impact of delta H on delta G. So when delta H and delta S are working against each other, which we'll talk more about in class, that would mean that you have to consider temperature. Okay, but let's consider, for example, this situation. H2O solid goes to H2O liquid. And I'd like you to take a moment for you to consider the signs of what delta H is and what delta S is for the process. So go ahead and pause the video and consider what the sign would be. Oh, so you should have said that delta H is positive, okay, and that means that that the system is absorbing energy, which it would need to do when you go from a solid to a liquid. And then delta S is also positive because you have greater entropy when it is a liquid as opposed to when it's a solid. Okay, again, liquid has more microstate arrangements possible than a solid does. Therefore, if you go from solid to liquid, you're increasing the number of microstates possible. Now, if you think about this, at a lower temperature, the process is like, let's say negative, Let's say negative 100 degrees Celsius. Okay, the process, delta G, okay, it doesn't happen. It doesn't happen when the temperature is too cold. Ice does not melt into liquid, so delta G would be positive. Okay, now if you go to, say, 100 degrees Celsius, which is 212 degrees Fahrenheit, that means that delta G is going to be negative because that process is thermodynamically favorable at that higher temperature. Okay, and once again, I'm going to go more into that in detail when we meet in class and talk more about what the sign of delta H, delta S, and delta G is. So definitely make sure you are paying attention to when I'm lecturing about that in class. Okay. Now, it's very important to note that delta H and delta S are not dependent on temperature, so we can actually calculate the value of delta G at other temperatures, since these are not dependent on temperature at all. So we'll talk about that in just an upcoming second. Okay. All right, and when you take a moment to read through the question, so go ahead and pause the video and read this question, and then continue when you're ready to resume. Okay, so using your understanding of the material from thermochemistry, go ahead and calculate what the value of delta H is from the heat of formation in this column. Okay, so if you did this correctly, you would have gotten negative 1351.88 kilojoules, because delta H is usually measured in terms of kilojoules per mole. All right, now let's go and do the same thing for delta S, and make sure you understand that the units for those are in joules per mole Kelvin, and the moles will cancel out in a moment. So go ahead and pause the video, and using the same process, calculate the value of delta S. So if you did this correctly, you have gotten 92.32 joules per Kelvin based on this column. And notice that oxygen does not have a S value of 0, because S does not necessarily equal 0 at 298 Kelvin, which it would be for heat of formation and Gibbs free energy. Okay, so now the question is asking you to find if the reaction thermodynamically favorable under standard conditions at 25 degrees Celsius. So we can go ahead and put these together, and we can say that delta G is equivalent to negative 1351.88 kilojoules minus T. The temperature would be 298 Kelvin, and then delta S. And we need to convert this to kilojoules so that we keep our unit consistent. So that is 0.09232 kilojoules per Kelvin. And that will give you a value for delta G at negative 1379.39 kilojoules, which indicates that because delta G is negative, the reaction is thermodynamically favorable at 298 Kelvin. Okay, and we can now do the same thing for 10 Kelvin. So we can say delta G, and no longer degree symbol because it's not at standard conditions anymore, but you can still use the value of delta H and delta S, even though they were formed at standard condition, because they're not affected by temperature. So 88 kilojoules minus 10 times 0.09232 kilojoules per Kelvin. We'll go ahead and enter that in the calculator. And you'll see that at negative 1352.8 kilojoules, that's negative, and that also indicates that it is thermodynamically favorable even at 10 Kelvin. So now another way you can go ahead and do that same problem to find out what delta G is at standard condition is that we can use these values of delta G, the products minus the reaction. So go ahead and do that and pause the video and do the same way we did delta H and delta S and see what number you get. And if you did this correctly, you would have seen that you got negative 1379.28 kilojoules, which is very, very close to what we got when we used delta H and delta S to find the value a delta G at 298 Kelvin. So I wanted to emphasize that as long as you are at 298 Kelvin, you can use the delta G degree symbol. But if you're not at 298 Kelvin, then you have to use no degree symbol for delta G, because again, the degree symbol indicates specifically at 298 Kelvin. So I hope that makes sense to you. Okay, so the last big concept is relating the equilibrium constant K to the value of delta G degree. Okay, now it is important to note that the K, when K is greater than 1, that means you have more product. And since that would imply that the reaction goes more to completion, then that means that the value of delta G, since you're going towards the product, that implies the delta G is less than 0. Okay, because that means more thermodynamically favorable, meaning more product will happen. So if K is less than 1, that means more reactants are favored, and delta G is going to be greater than 0, okay, which means less thermodynamically favorable. Okay, now a couple of things you have to make sure is that the gas pressure, K, that's used to determine for Kp, has to be measured in ATM. Solution concentration is going to be measured in molarity. And solids, liquid, and solvents are not included in the K expression. Okay. So let's see if you can apply this to a particular problem. Okay, I'd like you to take a moment to calculate what delta H is and what delta S is for that reaction. So go ahead and pause the video, and based on what you've learned earlier, calculate what delta H is and what delta S is. Okay, so check your work with this, and then go ahead and calculate what the value of delta G is, and the temperature would be in 298 Kelvin. So pause the video. Alright, so we should have gotten a value of negative 1490.2 kilojoules. Bearing in mind that you had to convert this to kilojoules. And let me make that correction right here. That has to be kilojoule. It was negative 543 joules per Kelvin, making that 0.543 kilojoules per Kelvin. Okay, so now we can plug this in to the delta G degrees equals negative RT ln K. Okay, delta G would be negative 1490.2 equals, okay, now negative R, you probably are thinking about the gas constant that you use in PV equals nRT, which is 0.0821. But when you're dealing with this one, when you're dealing with energy, you have to use 8.314, and then the unit for this one would be joules per mole Kelvin. But since we're dealing with kilojoules in this problem, we're going to change that to kilojoules as well to say negative and then 0.008314. Okay, again, I'd like to put the units in here. Kilojoules per mole Kelvin. I'm also going to put the kilojoules right here. The temperature being 298 Kelvin, and then ln K. And then when you run it through calculation, divide both sides by the coefficient of ln K, you get ln K approximately equals 601.5. And then knowing your exponential rules, that means K equals e to 601.5, which comes out to 1.65 times 10 to the 261st power. And that number is, of course, much greater than 1. So that indicates that the reaction goes essentially to completion. And this is actually the reaction that we were talking about earlier, the the process of rusting, which is iron reacting with the oxygen in the air to turn into rust. And you can see that this reaction does happen, indicated by the fact that the equilibrium constant is greater than 1, which really, in this case, is so high that it's really not an equilibrium. But that does go to say that you have a very high thermodynamic favorability for this reaction. Okay, so if you look down here, remember that thermodynamics, once again, determines whether a reaction is favorable, and the kinetics will tell us how fast it will go. And kinetics does not say anything about the favorability of the reaction, just like thermodynamics say nothing about the speed of the reaction. And I do know that this has kind of been a complicated lecture, and I've kind of been probably a little bit all over the place in some parts, but we are going to be talking more about this in class, so hopefully I can answer some more of your questions, and the thermo in-class question can also help you understand the material a bit better. All right, so have a good one.